Um, so again, today, what we would like to inform and have like a training session is more of on how we can recuperate energy from wastewater treatment plants and also water treatment plants using micro hydro turbines, and particularly using our technology. It's training is, number 13. Uh, as all of you know, it's basically to give you a bit of a background what will be the main essence for having this technology or generating energy from the wastewater treatment plant. But more or less, because the population is growing and there is also a huge demand to treat the sludge or like the waste collected from this growing population in the city, urban cities, most specifically. And this cause also the rise in cost of energy, particularly in some areas also fuel, in other areas other types of energy sources, which also cause to increase climate change, mainly for the CO2 emission. And this high energy demand for collection and treating of wastewater also needs an alternative source of energy. And then one of the source is the energy that's hidden in wastewater treatment plant facilities along its way from the collection up to discharging uh, back the treated water to the river. So normally it would be considered that there will not be any energy that could be recovered from such systems, but as nowadays with high electricity price, every kilowatt matters. So for that, we would like to also explore the possibility of energy recovering alternative energy from the wastewater treatment plants. There are some studies that mentions the energy demand for treating a sludge or like a waste, uh, which is range between 20 to 45 kilowatt hour per population equivalent. For instance, if you take, let's say, a 200,000 urban city, which contributes to the sludge to the treatment plant, this means we will need like annually between 4 to 9 gigawatt of energy for wastewater treatment. So this means there is huge energy demand, which needs also to be economically um, generated, and also it should be contributed to low cost of treating wastewater in the city. For instance, most of the energy is goes to the aerobic activity sludge management. By profession, I'm not an expert in wastewater. More of I'm on the hydraulic aspects of hydropower, but you will understand how much energy intensive the process is. So what we would like to emphasize more is what will be the possibility of energy recuperation from wastewater and water treatment plants, where we can contribute to reducing the energy consumption and make these facilities or plants energy efficient, as well as also save the greenhouse gas emission, which leads to climate change and leads to, in some areas, very low rainfall, that means drought, and in other areas, very high rainfall, which means flooding. And then this energy generation can also try to be fit in the wastewater treatment energy demand curve. That's basically when there is high demand for energy, then we can also activate the turbines, or we can also use the turbines to follow that demand, because basically the turbines are working using the water. So then there is more treatment work available, or more water is treated, there will be yeah, relatively high energy generation from the wastewater treatment. Having said this, I would like to introduce a bit about the technology. That's more the background of wastewater treatment plants. The one that you see on the video is our turbines in Kenya that we commissioned 2 months earlier. But basically, Turbulent is a micro hydropower manufacturing company. We have like almost 46 turbines globally in 5 continents. We have an active project in almost 5 continents again, and we are a highly fortunate team of like 19 people, and then we start designing this innovative technology since 2015. And globally, we are working on a different projects. And the beauty of the technology is it can be replicable. It can be also scalable. So, for instance, our recent project, what we have in Philippines, has an install capacity of up to 720 kilowatt. It's not from one single turbine, but rather by putting a cluster of turbine in different settings. Meaning, when we have multiple flows, we can put them in parallel. That means splitting the flow. And when we have more heads, like higher than the head that we used for a single turbine, then we can put them in a cascade. And in that way, we can increase the energy generation at a particular project. For instance, for the wastewater treatment plant, there will not be more flow, but there will be relatively, depending on the plant design, um, more heads. So in that case, we would prefer to put them in a cascade, one next to the other. You can access more information on the website. Of course, will not spend much time on introducing the company, but I would prefer to stay more on the technology side. So basically, it's a vortex turbine, meaning that it will need creation of a vortex. For that, we will use this spiral structure, which can be built from either concrete, metal, or brick, or even masonry, depending on the local material availability and cost effectiveness. The beauty of the technology is it's simple civil work and simple maintenance. That means we need the basin that you see on the right top, which has a trash rack at the inlets and also a sluice gate. So basically, what will happen is we will open the sluice gate whenever there is enough flow to rotate the turbine or to move the turbine, and then the turbine basin will create a vortex that's basically like a spiral hole. When you open your, let's say, sink or maybe hot bathtub, if it is full of water, and then if you open it, it will create this swimming pool, and then underneath we will put the turbine, and then that swimming pool will rotate the turbine blades, or like the impellers, and then there is inside this hub a generator which will be which is coupled to the impellers or just like the blades, and then there will be energy generation. So everything for except the electrical cabinets, everything will be underwater, meaning that it's compact and less maintenance, as well as there is no any noise for the environment. In terms of civil work, what we need is this basin to create a vortex, as I said, and a couple of lengths of inlet and outlet canal. Basically, that's what we need. We don't need a dam. We don't need a weir. There are sometimes that we need a weir, but basically to divert the water to our basin. That's in case of like small rivers and canals. In that case, maybe we may need a small width just to divert the water. Other than that, what we need is a couple of meters on the inlet side and then on the outlet side. That means head race and tail race in a conventional hydropower. So in terms of scalability and durability, we are by far the most yeah, scalable turbines, I would say, because of the very low head and very low flow range that we are working. So for a normal river flow or small river context, we need a flow of starting from 1.5 meter cube per second. And for the head, it's the same time 1.5 meters of elevation difference between water level and water level. But for the wastewater treatment is we have small turbines. So in the past that we have installed, which I will show you in a couple of slides later in the use cases. But what we need for a small and medium-sized rivers is basically for generating high energy. We need to have a flow of like 1.5 meter cube per second. But for the wastewater treatment plant, because there will be the availability will be quite limited, so we have like a range of low flows for that particular market, which as well in the past, and then now we already standardized our technology. So far, we have five standard turbines. Recently, we added another one. So from 15 kilowatt, 1.5 up to 90 kilowatts, meaning we already standardized our technology so that it will be ready to be manufactured whenever we have a head and flow that matches that particular turbine. This way, we can also reduce the overhead cost and also make it more affordable. The last but not least is its fish friendliness. So we are working in a very low head pressure. That means the changing pressure between the inlet and outlet canal is quite low. That means fish will can pass through the turbine without any significant harm or also stress. The other advantage regarding to fish friendliness is the spacing between the blades, which is quite wide, up to 256 millimeter. Additionally, there is no also pressurized hydraulic condition on the turbine during energy generation. It's more of free or atmospheric flow condition. That means there will not be any cavitation that also harm the fish when there is a migration from upstream to downstream. So these are the main characteristics, but the most important one is it can generate energy 24/7, which has high plant factor compared to solar and wind, which are more intermittent. This high plant factor will also leads to more energy generation during the year, which also reduce the levelized cost of electricity that needs to be invested for per kilowatt hour energy generated. So these are basically the highlights of the advantage of our technology. When we come back to the wastewater and water treatment plants, there are certain parameters that we need to take care of to install our micro hydro turbine technology. The first one is rate of flow, which is the available flow. When we say rate of flow, it has two main parameters. The first one is the quantity. That means the mass of flow per in metric per second, and the other one is variation. So how it vary during the day, the month, and a year, because that's mainly the main factor for the amount of energy that could be generated from this, let's say, facility or wastewater treatment plant. So in that case, I know the water availability in most of wastewater treatment plants, it's really highly variable during the day, but we have to capture and then we can also select a specific design value which can lead to optimize energy production. So that is the main um, characteristics that we need to know when we think of micro hydro turbines. So for the specific case nowadays, we want to standardize also our turbines for this particular market, which up until now we have done already pilot projects, which I will show you in a second. But for you also to have in mind, we need a minimum of 1.1 meter cube per second for our standard turbine to be installed in a wastewater treatment plant. This is the design value, but that doesn't mean that whenever the flow is less than 1.1, let's say, meter cube per second, the turbine will stop generating. It will generate, but it will not generate the design power. That means, let's say, if the turbine is 8 kilowatt, for instance, for or 10 kilowatt for this particular flow that we are considering, then whenever the flow is less than 1.1, it will generate maybe 6, 5, or 7. So this we will analyze during the feasibility stage of the project. But you have to keep in mind that we need, at this moment, we need to have 1.1 meter cube per second as a minimum flow to install a turbine in a wastewater treatment plant. The head, we prefer to have it also more or less in the same category, which is also 1.1 meter to have more or less like a linear relationship with the flow. That's basically also our uh, energy generation characteristics. The other most important parameter is the water quality. When we say the water quality, most importantly, what we consider is the salt concentration and then the chloride. You have more knowledge on this, some of you, so you can more relate to the subject. But for us, the most important part is the cabling, for because I told you the turbine will be inside water, beneath the basin surface, let's say, and everything will be underwater. The cables, the impeller, even the generator will be underwater. So we want to protect and then also have like a very long working period for these metal plates and the impeller and also the cabling for transferring energy or power from the generator to the electrical cabinets. So up until now, we can perfectly work in a salt concentration, which is 35 gram per liter. And for the chloride is basically to the corrosiveness. So what we will do is basically we will analyze the water quality. We will get this information from wastewater treatment companies or owners or any entity that we are working with, and we will analyze how the lifetime will be affected by this salt concentration, chloride, and other chemicals. The temperature, the normal temperature that we would like to work is between 0 to 40 degrees centigrade. But when we consider the different locations in terms of installing these turbines, I know these parameters may be different along the treatment process. So when we also look for installation location, that we will discuss also, we need to consider also what will be the parameters in along the treatment process from the collection point, let's say, to up to the discharging point in the outflow box. As you can see in the picture, we would like to show at what means the head, just to have like a clear idea, because some of our customers, for instance, they measure the head from the bottom of, let's say, a canal or a river, or in this case, the outlet box, up to the top level of the water. But what we need as a head to generate electricity is the elevation difference between water level to water level. And then the one that you see on the right corner is our turbine in metal basin in Versailles, in France, which will lead me to the next parameter that we would like to consider during identifying suitable site for our turbine installation in wastewater treatment plant. That's the space availability. So you might think of different locations where there will be a hydraulic head in the path from the collection to up to the discharging point in a wastewater treatment plant. So one of the constraints will be, of course, the parameters that I mentioned earlier, but the last, but not the least, is the space availability. So what we did in Versailles, which I will discuss also later, is we try to find a space for our turbine in the outlet box, because that's already where they head, and there is no enough space to also modify the outlet box to accommodate our turbine technology. So these are the main parameters that needs to be considered when we identify a site for micro turbines in a wastewater treatment plant specifically. What data that we need? I already mentioned how the variation of flow in the wastewater treatment plant will affect the energy generation. So for this, we need to have a flow duration curve, what we call it normally, which where we can see which flow is available for how much percentage of the time. And then in that way, we can find optimal turbine size based on the design flow. And then we can also estimate what will be the expected annual energy generation capacity from that particular wastewater treatment plant. So that's one of the main input that we need, the flow duration curve. This is basically, you will have it because you are measuring every day the flow that's coming and going out from the wastewater treatment plant. Then in that case, if you have time series data for the past, let's say 3-4 years or even more than that, and then if there is also population growth in the city that is expected, if it is significant, then we can also consider that future increase in flow availability, and then we will pick a design discharge that will have a higher energy generation compared to the other parameters. The other one is space availability. I've already mentioned. For that, normally the ideal location is the outflow structure, which is a discharging point. But in that outflow structure, you might consider like two ways I would prefer. The first one is, as you can see in the picture in the middle, which is a treatment plant in Lille, France, that we were analyzing. The first case is the head between this is small channel and then the outlet box. So this is one option. The other one would be if there is also extra head between this outlet box to the water level in the body of let's say in the river, which this flow is going to join, let's say if there is a nearby river, and then if there is a head between this outlet box and then the water body that receives the treated water, Then in that case, we can also consider that heat to generate electricity. The other most important parameter also in terms of space availability is accessibility for maintenance. Even though our turbine is less maintenance, which I can also give you more information, but medically every year what you need to do is changing the gearbox oil, and then also check every 2 to 3 years the cabinets. But other than that, we design it to be less maintenance intensive, I would say, because we're also targeting remote areas, communities which are far from the main grid or the national grid. So in that case, there will be first mobilization issue. Second, there will not be personnel who can understand or like who are a technical person to carry out these maintenance activities. So for that, we design it in a way that it will have less maintenance work. So for that, the space consent need also to consider the mobility of the personnel for the maintenance work, even if it's quite rare. The other parameter is, of course, the financial viability of the project. For that, we need to know the price of electricity that you are currently paying or what you would like to save. And we can compare that with the capex, basically the cost of the turbine, the cost of the civil work, and other workmanship that needs to be done to install the technology in the wastewater treatment plant. Uh, then, how the turbine will be installed. This is quite pretty simple for a wastewater treatment plant. Of course, there will be a mobilization and also accessibility issue, but basically, the first parameter or the first constraint is space availability, as I said. But in terms of permitting, when we consider wastewater treatment plant, it's mm, always, we can say, or just like mostly, there will not be any permit in terms of environment or water use because it's already a facility that exists, so there will not be that much permit for installation. But for the energy generation and also selling that, you need to have a permit. So in this installation process or in the project lifetime, we need to consider as well the permits to connect it to the grid if it is going to be on an on-grid turbine, and then if it's off-grid, then you will be isolated from the grid, and in that case, you might not need for grid connection permits. But if you are thinking to save the energy consumption of your wastewater treatment plant, or if you have an intention to save depending on the country context in the energy rules and regulation, then in that case you might need an IPP or a PP agreement with the utility companies in the energy sector. But basically, what will be the main process in the installation is once the contractor or the wastewater treatment plant performs the civil work where we are producing the technology or the solution, then what will happen is we will make sure the turbine is constructed according to the design, and then there will be commissioning and installation procedure that will follow to make sure the turbine is installed according to the design in a right orientation with the perfect angle to the turbine alignment with the civil work and everything. And then finally, we will insert the turbine in the basin to generate energy. Here you might see two different pictures. The one that I put in the middle is from the Alicante, it's a small turbine. And the other one that you see in the design drawing is the standard turbine that we have, where the generator is inside the impeller. But in this case, this is the old turbine model that we have. The generator is mounted on top of the turbine with connected with the shaft. So these are basically from the space availability and also the size of the turbine that we now shifted to be more compacted to a submersible generator. So these are basically the process for the implementation steps. Once we fix the size of the turbine, and then when we manufacture it, simultaneously the civil work can be done on site. Then when we finish the manufacturing, the civil work will be ready, and then we will install and start to generate electricity. One important aspect from our side that I would like to share with you is the accessibility of our energy generation facility, let's say micro hydro turbines, remotely from wherever you are. So we have an IoT remote monitoring system. For instance, the Alicante project as a modified, not a standard base, because also it's a small and not standard turbine, but we can also access any of our turbines all over the world remotely. So we have a remote monitoring system which can be accessible from your computer or mobile. Basically, you can see what's going on the micro hydro turbine, how much energy is generated, what is the temperature of the generator. There are a lot of sensors, so you can access to those information, and then you can even stop, start, or like close the sluice gate, open the sluice gate, whatever you want. You can have it also on your device. That means you don't have to assign someone to be there for the operation and monitoring of the turbine. Having said this, I would like to take you to some of our case studies or best practices. Um,
Samuel, can I just
yes,
ask a question?
yeah, sure.
The software, is it also on your side? Do you do the development or is it
Yeah,
outsourced?
no, it's we have here an IT department that develops this software on IoT based. So we are not outsourcing this work; we are doing it in house. So whenever there is a specific demand, as I said, for instance, when there is a cluster of turbine installed, then we have to put also other parameters for optimal energy generation. So we are doing the software development also in house.
Okay, perfect.
Perfect. Thanks.
Thanks.
You're welcome.
I also have a quick question, if that's all right.
Yeah, no worries.
Um, is it possible to, if there's a local automation company, can they also take the data and use it in their software, or is it locked to this software that's been developed? So you would have to use this software in order to, when you're using the hardware.
No, yeah, that's a nice question actually. So, our software, it can also be integrated to the SCADA. So couple of projects that we have here also in Belgium where we are based. In case if I didn't mention at the beginning, so we are working also with water authorities where they also control this existing routes for navigation purpose. So in that case, they would like to also consider have information, let's say, or partially or indirectly control the energy generation because it also consumes water during for navigation purpose. So their main priority would be for navigation purpose. So in that case, they have access to this data where they can see also how much water is going through the turbines. So it can be integrable to a SCADA system if you have, or you can also make it accessible to, let's say, by the facility if the wastewater treatment plant want to integrate this control software with their existing monitoring software, then that can also be doable because we have also in-house flexibility to do a custom design for specific demand for each project. So it can be accessible.
Perfect, thank you.
Yeah, so for the first one would be the Alicante, what we already introduced last time. So it's the smallest turbine that we ever built. It's a 2.5 kilowatt. It's a pilot project for for wastewater treatment and also for a small creeks, let's say, very small canals that can be replicable also in irrigation infrastructures. So it's relatively expensive from its size to be also clear. That's also one of our findings after we have done thorough analysis on the manufacturing and as well as the designing work. The head that we used for this particular turbine is zero point 0.8 relatively higher compared to the flow, which is 0.37. It's a pilot project, but the inherent property of the technology, we are using stainless steel for these metal plates, and then relatively from the project, we found it will be a bit expensive for this turbine size for 2.5 kilowatt. It's perfectly working up until now. If there is any yeah, up-to-date information, maybe Eric, you can also give us some information on this particular project. But as far as I know, it works fine. It's also an all-grid or off-grid setting. That means it works when the turbine is connected to the grid or when it's not connected to the grid. So it has a flexible option. So that's also what makes it a bit expensive to mention, because it can work both on off grid settings. So whenever the grid is down or disconnected for some reason, then the turbine can generate energy. Because in normal on grid turbines, so it will be synchronized with the grid. So whenever the grid is down, the turbine will also stop generating energy because it's synchronized with the grid. But in off-grid case, there is no grid. Our turbine will be a grid-forming turbine. Or if there is also, it's a hybrid off-grid scenario with solar, either the solar or the turbine will create the grid, then one or the other will follow that grid frequency. So in that case, unless the turbine is stopped working, there will not be any disruption of energy in off-grid context. But the third one that we are using is on or off-grid. That means you can generate following the grid frequency or the grid behavior. But whenever the grid is down, then you can also switch the off-grid mode, and then the turbine, the UPS that we will use has a device, then it will disconnect also what's connecting the turbine to the grid, and then it can also give energy to your mini grid or your facility that you'd like to protect whenever the grid is down or a load shedding. So this is one of the main uh, separating point, I would say, for these small turbines in wastewater treatment plants. The other project that we have done in the past is the project in France, in Versailles. It's a 5.5 kilowatt. It's also an old model,
Sorry,
as you can
well,
see. Yes.
before you go to the next one, yeah, I just wanted to say that regarding the pilot in Alicante,
Mm-hmm.
I was not like super involved in this pilot. I was more involved in the other ones, but
Okay.
the number I had in mind regarding the installed capacity of the pilot was rather 2 instead of 2.5. And yeah, after all this time and seeing the capacity numbers of this turbine,
Mm-hmm.
we've basically seen that the contribution, the potential contribution of this pilot to the self-sufficiency of the wastewater treatment plant is really, really low
Yeah.
compared to, I don't know, like the anaerobic digestion and other renewable energies that could be implemented in a wastewater treatment plant, at least in a wastewater treatment plant, not like super big. That's the main thing about Monte Orgegia, which is the wastewater treatment plant that we installed the pilot.
Mm-hmm.
And what we considered at some point of the project was, instead of connecting the pilot to the energy grid of the plant, it was to connect it to some sort of batteries from which we could fuel electric cars, but it was not done eventually.
Okay. May I know why it's not done for charging the vehicles?
Because of money issues.
Okay. Yeah, but it's really nice that you shared also how the contribution of the energy from our turbine is not significant in your case. But I understand it's basically with the available flow and heat, and also how much energy you can extract from these flows. But in terms of install capacity, we are mentioning the install capacity usually based on the generator capacity. So I think that's where the difference comes from. But I will check also with with the numbers that I have here, and then I will correct it for if it is only 2 kilowatt. But as far as I know, we are using always the installed capacity means the maximum you could go based on the generator capacity. So that's it. But I think it would be nice, maybe also for future, to have like a comparison of other energy sources in the facility that you are generating currently. I remember there was also a kind of biogas or biomass on Alicante for energy generation.
Yeah, yeah. There's actually because if you remember, we visited a couple of wastewater treatment plants.
Mm-hmm.
The Rincón de León, where we had the rest of the pilots, is much bigger,
Mm-hmm.
but it also has like a small desalination plant, which has like a big energy consume. So
Yeah.
anyway, in terms of specifications, we didn't install that there, but we have biogas production in both of them.
Okay.
And the biogas contribution to the energy self-sufficiency of the plants is much bigger.
Bigger than, okay. Good to know.
Yeah, I would say that the biogas contribution would be around the 20% of the energy consumption of the plant,
Okay.
and the energy that we could produce with a pilot was below 1%.
Yeah. Yeah. That's good to know. But yeah, basically it's in terms of I would say flow availability for our case, because it's directly proportional to the generation, the power generated.
Mhm.
So I think that's one of the possibility, I would say, for low energy generation.
Just an additional question, maybe to both of you. I know that the size or the installed power in Alicante, it's not the common size that you install, but what's the payback period for the one installed in Alicante, and what's the payback period for a common one? Let's say this one in France.
Okay. I think that one, I don't know if Eric has done any financial analysis. But
Probably not the best case because it's a smaller one, but
yeah, it's
just
quite a smaller one. Yes, it's a smaller one. So I started at the beginning. I'd say it's expensive because of its size, and also because of its on and off grid, yeah, architecture. I can share rough costs. Now, if we have to replicate this technology, the one that we installed in Alicante, it might be in the range of between 30 to 40,000. So for that particular size, that's what we are saying, it will be expensive. Because I can tell you, for instance, if you want to install much bigger size, let's say in the wastewater facility range, if I give you yeah, like let's say rough estimate for like 8 kilowatts, you might need like up to 50 to 60,000. So you can imagine, with a small increase in budget, you can almost double the energy, the power generation. So for this particular case of Alicante, we already assessed, and then we found it would be expensive to install that turbine size. So we are not anymore looking to install that turbine again, to be honest. That's one of our conclusion and findings. But for your second question, the normal payback period for our turbines between 4 to 8 years maximum, from our past projects that we have seen. But of course, it depends which country and then what type of situation that you are considering. Meaning, if the electricity price is higher, then your payback period will also go down. And in some cases, even if the electricity price is not that much significant, but if there is a load shedding, let's say, for instance, in the case of South Africa, there is a lot of load shedding in the country. So for your, let's say, manufacturing company or any other energy needs, would you like to have more sustainable or like reliable energy source, which will be there, yeah, no matter what, or would you like to have energy from the grid, which you may not have any control of for your energy demand. So that's also one trade-off that you would like to see. So normally we are considering all these scenario. The other one for factor that will affect also the payback period is whether you are installing multiple turbine or single turbine. We are always in favor of installing multiple turbines because in that case you can also reduce the cost for electromechanical, because we can combine up to 3 turbines in one single cabinet. But if you will install already one turbine, then you will have also one single cabinet. So these are the main factors also that needs to be considered when we do the payback period. But normally it's between 4 to 6 years. And the other factor also is the civil work, as I've already mentioned. For instance, in here in Belgium, we have already finished in 6 months the installation and construction of 15 kilowatt turbine. So that's also fast installation, which will also reduce the cost and the mobilization. So these are also the factors that I would like to mention that we need to consider to take into consideration while thinking about the payback period, I think I answered the question, right?
Yeah, thank you.
Yeah, perfect. Yeah, so for Versailles, the main point that I would like to mention is the flexibility that we showed to install the turbine in the outlet box. So as you can see, these are the only space that they have at the time to install this turbine. It's a 5.5 kilowatt turbine. And we have done already a small design to accommodate the the special requirement of the turbine. So what we did is we built this small division in metal just to also guide the water to our inlet. So this is basically as an inlet canal, and then we put the turbine underneath, and these are the metal basin to create the spiral or the vortex action of water. And then the water, after it generates energy, it will go to the river. So this is the treated water. So here, what we would like to mention basically is we can build a turbine basin from metal or concrete, or also brick, depending on the material availability and then the cost of construction. So it starts generating energy from 2020 up until now, and then it's also on grid turbine. So if the grid is down, then the turbine will also stop generating power. The parameters are basically 1.3 meter head with 0.7 meter per second flow, and this is also the earliest models when we use for the blades cast iron, not stainless steel. So we evolved so much from this model as well. So it's not already in our shelf to sell such kind of turbine. This is not in wastewater treatment plant, but the size would also be in the same range. So we can have the head and the flow range also for this. It's also in Estonia. Maybe here what I would like to mention, or the main special feature about this turbine is we have tested it to generate energy in a very low temperature. So we are monitoring the turbine, and it's for the chicken farm. So the customer has a chicken farm, so he wants energy to warm the chicken and the facility during winter, where there is also enough flow for the turbine. And then we have seen the turbine was generating up to -5 degrees centigrade in energy, so that means the lowest it could go. But of course, if the environment, or let's say like the temperature in the environment is going up to also -20 degrees, it also generates energy. So the main factor for us is the temperature of the water, not also temperature of the surrounding. But we have already demonstrated it can generate energy up to -5 degree centigrade.
Samuel, can you elaborate a little bit on that part of the temperature? What does this entail? The fact that it can work in negative temperatures? How how does it work? Sorry for my question, but it's
No,
like
no, no, it's okay. It's okay.
someone who comes from the outside, you know.
Yeah. So that means normally I'm not a mechanical engineer or electrical engineer, but whenever the temperature is there is already an ambient temperature, that's the all the cabinets, the generator, the cabling will work. So whenever you are going down, then there will be an impact on the performance of the generator, the cabinets, the electrical cabinets, which has all the breakers and everything, and also the cabling that takes the power or the energy from the generator to the electrical cabinet and also to the grid connection or your house connection. So that's basically how it is. And then if it's froze, then of course everything will freeze, and then the turbine will also stop generating energy. So it's basically from the generating energy perspective, and then also from the performance and the long life perspective of the turbine.
But
That's
well,
basically what I would like
the
to
thing
say.
is that below zero, water freezes, right? So
Yes.
there has to be some way of heating the
Uh,
water flow, or is it
No,
crazy?
if the water is yeah, that's what I'm saying. Like it's mainly the temperature of the water. If the temperature is
Oh,
below
okay.
zero, then the water will freeze, so there will not be flowing water.
Okay, sorry, I didn't understand that part.
No
Okay,
worries.
great.
It's not the surrounding temperature, but basically the temperature of the water. So if it is below zero, then
Okay, so this is the norm in this kind of equipment, right? If anything below zero, it's
yeah, normally
no
I
way,
think
right?
if I go back, I put temperature range here. So normally for our technology as here, you can see between 0 up to 40 degrees centigrade. Is that like the ambient
Okay.
temperature that we would like to see? But what we have seen on site for this particular project in Estonia is when the surrounding weather, like let's say the temperature was below 9, if the water is still flowing, then the turbine can generate
Yeah, sure.
energy. That's what I would like to
Yeah,
share.
yeah, yeah.
Sorry if I misled you. Huh?
No. Thank you.
Yeah, no worries. This is the last project that we are working on. It's still under study and design. It's a project in Phoenix, Arizona, in the US. For this particular case, we are targeting the biggest turbine that we have, 50 kilowatt, but as I said earlier, it will generate between 8 to 10 kilowatt, depending on the available flow. So now to cut also our overhead, we already standardized our turbines from the smallest 15 kilowatt turbine up to 90. That means 50, 30, 50, the first one 15, sorry, and 70 and 90 kilowatt. So we have these 5 standard models to not to have every time a custom design, but you can also do a custom design. This is basically to make it more affordable to our customers. So it's still under design. So hopefully next year we will have the production if everything goes well. So this is the last project that we have on currently on wastewater treatment plants. Yeah, basically this is what I would like to share with any of you so far. If you have any additional question, can still discuss. Thank you for your patience and attending this session as well.
Yeah, I have a couple questions that I just wrote some rough notes, so I'll go through if that's okay.
Yeah, sure.
One was, how long would you expect the life expectancy to be for one of these turbines?
Perfect. So normally we are designing it to last between 30 to 50 years, technically depending on the working condition of the turbine. And there is already a maintenance that we already proposed. Maybe I think it would be nice to show also that maintenance slide, I think. Sorry, just stop sharing quickly. So I don't know if you can still see my screen.
Mhm.
Did you see my screen?
Yeah. Yeah, you can see.
So this is the quick maintenance guide that we have. So for the operation and maintenance, it's in the range of like 1 to 2% of the capex, the core capex. That means the turbine and the cabinet. So this is the final delivery that we will send to our customer, like for the project. So you will have this turbine and then the cabinet. So we are designing it to last between 30 to 50 years, but there are always some maintenance that you need to take care of because our metal works are from stainless steel, so which can last for long. And then the other ones is basically to check the gearbox oil, the electrical cabinets, and the battery replacements, and fasteners check for the tightness of the generator. The most let's say relatively expensive maintenance would be the genset, which means the generator with the gearbox. So that one needs to be inspected well, and the manufacturers, we are the suppliers, I would say, of the generator is from Germany. Basically, if it works under like a normal condition, it will last more than 15 years normally. So the whole turbine can last between 30 to 50 years. And then that's what we are also monitoring every time when we have a project running. We have all operation data from our sensors, and we always examining how their behavior during energy generation. But basically, that's the range in terms of lifetime.
Yeah, and I was wondering, what is the protocol used for the system? So if it were to be integrated into an existing SCADA system, what language does it speak, per se?
That's quite specific for me. What do you mean by language? Like these IP protocols? You mean?
Yeah.
I can share with you the information if you want, but I don't remember by heart. But there are like IP 48 for the generators. I can also quickly check. Then I can also tell you for the cabinets. Yeah, it's IP68, for instance, for the protection. But for each component, there is already an yeah, IP or standard that we have. But I can share it with you also specifically for each component that you'd like to know. Basically.
No, it doesn't need to be so detailed, just general. Yeah,
Yeah.
and then with the software, is it something that you'd have to pay for monthly, or is it something that comes with it, or?
Nice. That's, I think, it's a nice question. I missed that part. So normally, what we will do for the monitoring software is we have annual fee. So we will charge you annually, but the first year will be free once you install the turbine and running. But after that, annually we will charge based on energy generation. So whenever you are generating energy, you will pay. If not, then we will not also cost you. So we tied it with the energy generation, which is 0.005 euro cents per kilowatt hour. That's how much we're charging annually for the monitoring and software.
Yeah, I think that was the main questions.
Perfect.
Yeah, thank you.
You're welcome. No, do you have any other question?
No, I don't think so. Just one observation, kind of a question. Like, so the main feature of this type of micro turbine is creating the flow, right?
Yeah.
That's where the difference is made.
Yes, the flow, yes.
Yeah, because that way you're able to produce more energy than you would without it. Like if there was no mechanism for creating the vortex, the flow would be lower, and the energy would be lower, so it wouldn't make sense. So this way, it's the optimization of production, right? That's the
Yeah.
main concept of the.
Yeah, the main concept of the technology is basically related to the vortex. So you have to optimally create the vortex
Yeah.
to generate, let's say, optimal energy. So if the vortex creation is not efficient, then the energy extraction will also be efficient.
Yeah.
Because that's inherent behavior or like principle of energy generation using
Yeah.
vortex
Yeah.
turbines.
Yeah.
So that's what also it makes it different to power plants, let's say, because for them it's like an impact. Or if you consider uh, the other turbines, like let's say for Archimedes screw turbines, or also very high head turbines, which basically work on impact. So you just
Yeah.
have to, yeah, hit the turbine blade and rotate it. So it's
Yeah. Yeah.
it's the principle is the same, but the driving force for our technology is basically the vortex. That's great.
Yeah.
That's what I
Yeah.
show.
Yeah. It's quite clever.
Thank you. Yeah, for the low hit, yes. But what I would like also to mention is as we go higher, this is basically for let's say mini hydropower up to. We will also recommend between 1.5 megawatt to 2 megawatt in terms of clusters of turbine. So whenever you go higher than that for a particular project, then it's better to consider also other technologies, because we are limited in terms of size per turbine. So if you want to generate, let's say 3-4 megawatts per turbine, then we are not that type of technology.
Yeah. Sure.
Yeah.
Yeah. Makes sense.
Perfect.
Okay.
If you have any other questions, still I'm happy. But I would like to mention also to fill, I think it's also one of the requirements to fill an evaluation. I will put it in the chat box so that you can fill the form and then give us also feedback about the training or any other comments that you would like to share with us. Yeah.
Okay.
Perfect. Any other thing that you'd like to know?
No, I'm good.
Covers.
Perfect. Yeah. Thank you so much. So I don't know how I will share the recordings, but I think it would be available on the next cloud project. So maybe yeah, I'm asking for the meeting recordings.
Perfect. Thank you.
Okay.